Now it's going to be the second part, the second lecture of Professor Daniel Scheeres, which is entitled The Mechanics of Rubble Pilot Bodies.
Okay, thanks for, again, the invitation to come and participate in the school, and the freedom to sort of present a range of topics. So what I'm showing today is actually research that initially came out of some of the questions that we were trying to understand, just based on exploration or satellite exploration of small bodies. And what we found when we did that work was that many of the properties of these small bodies were largely unknown, but very important in order to appropriately design sort of an exploration approach, or to understand which assumptions you could or could not make about what the environment around these small bodies were. And at the time when I started working on this, almost 20 years ago, if you had asked the planetary scientists, well, what happened, what assumption can I make here, what should we do? They would largely say, well, that's an interesting question, but I'm busy, doing other things. So it was realized it was sort of an opportunity to start addressing and understanding what some of the sort of the principles of evolution and development of these very small asteroids would be. And in the intervening time, they've become a bit more popular with people realizing the impact risk and with additional exploration missions to these bodies and the like. So it's really grown into for me, a very satisfying additional area of research where I've been doing quite a bit of work. So I'll just jump right into the topic. And what we're talking about here are commonly called rubble pile asteroids. And in fact, most asteroids are thought to be rubble piles. And what do we mean by a rubble pile? It's a size distribution that goes from very fine dust, maybe microns in size, all the way up to boulders that could be tens of meters, if not 100 meters in size. Across, so these bodies are not just single entities, but are actually collections of bodies. Similarly, a mountain is not one big rock. A mountain is the size distribution of dust all the way up to large boulders. The spin periods of these bodies goes down to about 2 hours for bodies larger than roughly 500 meters, and for bodies less than 500 meters, it actually goes much shorter, where they spin much faster. And we believe that they hold themselves together primarily with gravity, but as I'll talk at the end of the lecture, we also have some evidence, at least, that at the smaller sizes, other forces, non-gravitational forces, such as just the van der Waals force, can actually play an important role for the evolution of these bodies. So what I focus on here in this talk are on the so-called small asteroids, which are of size less than 10 kilometers. And this the distinction is important because once you get below 10 kilometers in size, asteroids are susceptible to what's called the Yorp effect. That stands for Yarkovsky, O'Keefe, Redzivitsky, Paddock. And it's a very interesting phenomenon that I could give a whole set of lectures on by itself. But all you need to know for here is that what the Yorp effect tells us is that sunlight or solar radiation pressure shining on an asymmetric body that has some rotation rate can cause that body to increase or decrease its spin rate. It applies a net torque on that body. And it's really no different than how the wind, when it hits a propeller, which is an asymmetrically designed object, causes the propeller to spin because there's a torque. So the sunlight does the same thing with an arbitrarily shaped bodies, such as asteroids. And this is important because it means that these spinning rubble piles don't remain static in terms of their spin rates, but their spin rates actually change over long periods of time, but very short periods of time in terms of the solar system dynamics. And thus they go over variations in their spin rate over the lifetime. And what becomes very interesting is what happens when their spin rates get large. And that's a prime focus of a lot of research related to the Yorp effect. So the fundamental question that I'm looking at in this work is how does basic celestial mechanics influence the evolution of these rubble piles? And the short answer is that it turns out that basic principles of celestial mechanics are extremely significant at all points of their lives and for the whole range of different body sizes. And in fact, you can use concepts from celestial mechanics to actually analyze almost the full range of these bodies. So here's another look at the small asteroid population, or actually this is actually just the asteroid population. Here we have diameter going from on the order of 10 meters or less all the way up to 1,000 kilometers. And you'll see this diagram a lot. And here we have plotted the rotation period. Shorter rotation period or faster spin rate as we increase, and then longer as we go down. This is a little bit out of date, but the main picture remains the same. We see that for larger bodies, there's actually like a spin limit. We'll talk a little bit about that later on. Whereas for smaller bodies, there seems to be no spin limit. In fact, they can spin relatively rapidly. Also shown on here are the binary asteroids. At this point, there were only 131. There are more known now. They're the green spots. Significant that there are no binary asteroids at these smaller sizes. We'll touch on that. And also the so-called tumbling bodies. And these are bodies which are not in a uniform rotation state, but actually have a complex rotation state. And many of the larger ones actually rotate quite slowly, although significantly again, some of the smaller ones are in a complex rotation state, yet spin very fast. And we'll talk a little bit about that later as well. So how do rubble pile asteroids form? The basic theory is nicely summarized in this cartoon from Fujiwara's paper in Science relating to the Hayabusa mission to Okawa. You have a catastrophic collision between larger asteroids, which shatter one or both of those asteroids. And the debris from that large impact gets shot off, and some of it is actually in a capture radius around each other, and they actually settle back and recondense as as this collection of rocks and the like, and then settle down into what we call or consider a rubble pile body. We actually have some direct evidence about what these rubble pile bodies look like. This is mainly from the Hayabusa mission to Okawa. Very exciting that we have a few more missions coming up which will give us further insight into what these smaller asteroids look like. And here Okawa is clearly comprised of a collection of boulders and grains. On this body, the maximum boulder size is tens of meters. We know the minimum size is on the order of microns, and that's from the sample that was taken. And the boulder size distribution has been measured as a cumulative 1 over d cubed distribution, which is almost like an equal volume distribution. If you took one big rock and you kept on breaking it up into smaller and smaller pieces, following this law, you would actually conserve the volume. Maybe a little more representative is actually the pictures, which we actually saw yesterday. This is some of the smallest material, which is actually, this is 100 microns. Much of the material is actually less than this microns. And then a larger scale where this is tens of meters across, and we see these other large boulders essentially sticking out from the interior of this body. Here are some other close-ups of some of the rocky boulder fields on Okawa and on some of the gravelly smooth areas as well. Again, you look at this and you say, well, it's a pile of rocks. Okay, so with this model and with the observations that we've taken of the population, we're actually have been able to start to construct sort of evolutionary pathways for these small rubble pile bodies. And this is a somewhat complicated plot. We'll actually go through different areas of this as I go through the talk. And it turns out we actually can, if we start with a single solitary rubble pile asteroid, and if it's subjected to what we call the Yorp spin-up effect, so it's caused to spin faster and faster, or its angular momentum is caused to increase, it will eventually go through some process that we would call fission, where it spins so fast that gravity can no longer hold the body together anymore. Once that happens, it turns out that there are actually three fundamental pathways that this body can evolve in, depending on how it splits into multiple pieces or two pieces, and depending on how large this body is. And as we go through, we'll actually talk about some of these different pathways and some of the significance that lie behind them, and really some of the basic celestial mechanics that has led to us to our understanding of how this whole population can evolve in time. So this is a sort of an interesting plot because most of these end groups eventually can actually be reset and come back in sort of a scale independent way when they're larger, and then when they get small enough, actually there's another process that takes over, which I'll talk about a little bit as well. So first, we could just talk about what I call fission mechanics of a rubble pile body. And the question is very simple, and the answer turns out to be rather interesting. What happens to a rubble pile subject to a Yorp spin-up, or essentially what happens if you take a rubble pile and very slowly spin it to a very fast spin rate? So you don't have to worry about accelerations, but it's just a evolutionary process where it continually spins faster. At some point, something has to change, right? So we know that the angular momentum of these bodies change over time. We're modeling them as a collection of rigid bodies resting on each other. And the study of these things are somewhat poorly understood, but this is a system that can exhibit very complex behavior. First of all, even as you start to spin a body faster and faster, we can have fundamental changes in how these resting bodies sit upon each other. And I'm not really talking about that in any detail in the talk today, but my talk at CELMEC actually looks at a very idealized case for the three-body problem and charts out what sort of transitions happen even before the body is spun apart. And these transitions happen at very discrete energy levels and can cause global landslides as material can seek out a new minimum energy state. If you continue this spin up, it actually leads to rotational fission of the asteroid. And this means that the asteroid has separated into multiple pieces, generally just two pieces. And what you have as soon as that occurs is you've gone from a single body to a binary system. We really call it a proto-binary because we don't know what the end state of the system is yet. Once that proto-binary forms, there are several different things that can happen. It can completely disrupt and form what we call an asteroid pair. It can re-impact and form a contact binary, or potentially it could form a stable binary. And then there are additional evolutionary effects that can drive how that body changes. So the simplest point you can make is by looking at the simplest system, two spheres resting on each other. And fission is just when these two bodies achieve orbital speeds relative to each other. And the first thing you can note is that the fission spin rate is a very strong function of the shape. And hence the energy of the system once it fissions is a very strong function of the shape of the distribution. So for example, if we just take two equal-sized bodies of equal density, we can calculate the spin rate at which these two guys will go into orbit around each other. And if we compare it to two other bodies of equal density, but one is much smaller than the other, and here we find that there's actually a factor of 2 difference between the spin rates where these two bodies will actually fission and enter orbit around each other. So this smaller guy will have a much higher energy and separate at a much faster spin rate, whereas the equal mass distribution will separate at a much slower spin rate and have a much lower energy once it separates. So even this simple example shows a very fundamental result that size or shape of the system matters very much in terms of what happens after rotational fission occurs. In the most ideal sense, if you have a collection of bodies resting on each other, you can really model fission as a very, almost a smooth transition process for a rubble pile body, where at one point it's spinning slow enough so that they're still in contact, and if you increase the spin rate by epsilon, at some point they will suddenly not be in contact anymore, and some important normal forces will go to 0. And maybe there will be a slight excess of centripetal acceleration. And at that point, that's a very smooth transition, but once that happens, the bodies will start to move apart from each other. And that precise moment of transition, ideally, is actually going to be quite smooth. And you can actually match up energy and angular momentum across that decomposition. So in terms of kinetic energy, before fission, you might have a single moment of inertia and spin rates for the spinning body. Immediately after there's some separation between two of these collections, you'll actually have two bodies with joint spin rates, which have not changed in that infinitesimal time period, but they each have their own moments of inertia, and you have a joint moment of inertia between these two mass distributions. So you've gone from a single rotating rigid body into two rotating rigid bodies which have an additional translational degrees of freedom as well. Now, of course, I1 plus I2 plus this component will just give you that initial moment of inertia. Potential energy is similarly decomposed. Initially, you have just the self-potential of that distribution. As soon as there's some breakage, if you will, or even before it breaks, you can arbitrarily draw lines through that connection or that collection and separate it into two self-potentials and a mutual potential between those two bodies. However, once fission occurs and these two bodies actually separate, you now have a mutual potential energy that's liberated in terms of this mutual potential between the two bodies, and actually serves as the conduit through which you can transfer rotational and translational kinetic energy between the rotational and the orbital states of these bodies. So graphically, here's a prototypical rubble pile asteroid with a self-potential U0. You can divide it, arbitrary line through here, and then we have two self-potentials and the mutual potential related to these guys. And if it starts to evolve, it will conserve its energy, but it will actually couple the rotational and the translational kinetic energies together with changes in the mutual potential. And we don't have to make this assumption, but things get easier if we make the assumption that that the self-potentials of these two bodies maybe remain constant initially. There are instances where we think that this definitely does not occur, but this is still a reasonable hypothesis to make just to study the fundamentals of this simple fission process. Now, if you think about it, if you have a collection of bodies resting on each other, and if you spin it up to a certain rate, fundamental question is, well, what pieces of the body will separate from each other? And in fact, when you think about it, usually the first time through, and I did the same thing, you think, well, the first thing that's going to separate is like the smallest piece of dust on the surface, or the smallest rock on the surface. And actually, that's not true. What actually separates first is, and I'll show you a representative equation in a second, but these bodies tend to separate in the center first, because that's where actually the stress is the largest, and where the mutual potential, in some sense, is reduced. So you can consider all the possible ways that this guy could fission. To actually show it, you can show that for an arbitrary rubble pile, if you split them into two collections, I and J, sequentially, the general condition can actually be written out like this in terms of the mutual potential and the centripetal acceleration between these two centers of mass. And you can actually go through and apply a weak form of Euler's theorem on homogeneous functions and actually reduce it to a balance between kinetic energy between two of these partitions and the mutual potential between two of those partitions. And you can sum it up in a very simple rule that the two components with the largest separation between their centers of mass will fission first and at the lowest spin rate. And this is, it's not a very precise statement, but it is a very useful rule of thumb that seems to definitely hold. So if we go back to Okawa, say, where we see it's really these two bodies resting on each other, if you apply that sort of a principle, what you see is that these two collections will actually have the largest separation in terms of centers of mass. And if you spin this body up, these guys should separate at roughly a 6-hour period. If you look at 1999 KW4, which is a binary asteroid, and we saw the movie of it yesterday, and if you just, naively froze this body, took that secondary, and just rested it on the primary, and then, spun it at an appropriate spin rate, what you would find is you'd have to spin it at about 4 hours, and then those two bodies would separate from each other. And in fact, we can simulate that sort of a phenomenon. And that's what this movie does. And what we have on and I'll show the movies on the right a lot, but this one shows the same dynamics in two different ways. So what I've done here is I've started the KW4 system, this ideal system, and this is a planar approximation to it using ellipsoids. And I've started it so that the smaller body is resting on the larger body in a minimum energy configuration. And I started with a spin rate that's just an epsilon above the fission spin rate. So these guys immediately fall apart from each other, and they start to evolve dynamically. And what you see is that there's a lot of coupling that occurs between the rotational motion of both bodies and the translational motion of the system as well. This is an inertial view of the system, and then this is a view where we fix the center, the radius from the center of the large body to the center of the small body, and this actually has a variable rotation rate. But then we look at the relative rotations of both bodies relative to this, and that gives us the plot on the right, which is in some sense a little easier to digest once you understand what the dynamics are. Now, this is an interesting result because it shows, this system, when it started off, was actually stable, just resting on each other, and it's almost like it falls off of a cliff, and it starts into apparently, at least to the eyes of the beholder, chaotic evolution of this system. And so this is something that we wanted to study a bit more and get a firmer handle on. So to do that, we can actually construct a very simple sort of toy model that has all the essential elements for this system. Construct a planar model of these two ellipsoidal bodies as they interact with each other. Here you see the degrees of freedom, the relative distance between them, this inertial angle, which is what we remove in that plot on the right, and then the relative rotations of each of these bodies to that radial distance. Construct a Lagrangian, and here we're just using a second degree in order expansion of the mutual potential, because that's very simple. We've continued this work using much higher order mutual potentials as well, but the essential dynamics that occur are really captured by just the second degree in order of this body. And this is an analysis we did some years ago. When you analyze these bodies, what you find is that there are actually two types of relative equilibria that can exist. There, of course, is an orbital equilibria that we're all sort of familiar with, where it's sort of like a gravity gradient situation, where you can have, say, the principal axes of these bodies lined up with respect to each other. If they have a given distance, you can imagine if you make the entire body rotate at the right rate, everything will be in equilibrium. Okay. You also have what we call resting equilibria. And this is a function of the total angular momentum of the system. Whereas if the system does not spin fast enough, it cannot maintain orbit around each other. However, it can still be stable, just as two rocks resting on each other are stable. And here, depending on the spin rate of this system, the resting equilibria can actually have different formulations. For any body, ellipsoidal body, that spins fast enough, it turns out that the resting equilibria that's stable before it enters this fission will actually always have the long axes of these bodies lined up with respect to each other. However, if I slow this system down to a much slower rotation rate, the minimum energy can actually have this ellipsoid resting on top of that ellipsoid. So you can actually see that if you take just these two bodies resting on each other, and if you increase the angular momentum over time, what may be a stable equilibria at one level of angular momentum can actually change and become unstable, and the body would then naturally seek out another equilibria. In this resting equilibria here, then if you continue to spin the body faster and faster, at some point, the normal force between these two bodies actually vanishes. And in fact, it becomes orbital equilibria as well. However, this orbital equilibria has some very interesting stability properties, which were already hinted at by that previous movie. So we can actually show these orbital diagrams in this somewhat abstract plot here, which actually covers a wide range of situations. What I have here are just two ellipsoids resting on each other. When they rest on each other, that's a unit distance, and that's that distance 1 along here. So this line is the line of these two bodies resting on each other. Here I have the normalized distance that's greater than 1, which actually defines all the orbital equilibria that these two bodies can have. And in fact, I can pick, and the mass fraction is just a measure of how the mass is distributed between these two bodies. 0, all the mass is in one body. 1, it's all in the other body. 1/2, they have equal mass, even if the shapes are different. Any point on this diagram can be an equilibrium point. So you have the mass fraction, you pick a distance, there will always be a spin rate of the system that makes it an equilibrium. Okay? What I have marked on here is regions of where we have stable relative equilibria and unstable relative equilibria. And in fact, this red line demarcates between where these two bodies would be in a stable relative equilibria and when they would be in an unstable relative equilibria. And it's very important to note that the touching, the resting equilibrium configuration, as soon as that becomes an orbital configuration, is always in the unstable zone. What this really means is if you take these two rocks, these two ellipsoids resting on each other, and you spin it up fast enough so that they actually enter this orbital equilibria, they will always be unstable. And you always get that initial motion that you saw in the movie, where as soon as they started to orbit, they flew apart and went into a seemingly chaotic orbit. A couple of other points on here, which we'll get back to. This conjugate solution here is the solution that has the same angular momentum as its counterpart along this resting line. And you'll see a different view of this in a moment. And what happens is this body has a higher energy here. So this is the equal angular momentum component to the resting component here. And each of these, however, have energies. Since this is unstable, it makes sense that this energy must always be larger than the energy of the second body here, which is actually stable. And this actually has some implications, which we'll touch on a little bit later. The other line that's of interest is what I call the Hill stability limit, and that's this blue dashed line here. And essentially, to the left of this line, or to the right here, the energy of the total system is positive. Whereas to the right of it, the energy of the total system is negative. And again, this has a very important implication. So here's another look at this, these equilibria. Here, this is for a given shape and mass ratio or mass fraction between the two bodies. Here we have the normalized distance or normalized radius, if you will. And here we have this red line is the line of equal angular momentum for this body. So what we have is if the spin rate is relatively small, the system is down here, wants to be along this red line, maybe, but is forced to stop because they're resting on each other. If you spin the system up fast enough, at some point there's this equilibrium that actually intersects the resting location. And the body, once it hits this point, actually is in an unstable relative equilibrium. Because of this resting limit to the left, it has to fall off to the right. And in fact, there's once it does this, it'll conserve its energy. And it's restricted to lie in this range here. And in fact, it will oscillate back and forth. And if it dissipates energy, which it can do just due to internal forces and internal interactions, but it has to conserve angular momentum, because that's really a more fundamental conservation principle. If it dissipates energy, it might rock back and forth and eventually settle down into this stable equilibrium, which is at the minimum of the energy level. And in fact, you can show even in a higher dimension that these relative equilibria, there's always a stable relative equilibria that in fact minimizes the amended potential, which you can use to study the stability of these systems. And the fission point always has a saddle point in that amended potential, meaning that it's unstable. So this is the case for the mass fraction to the right of this dashed blue line, or to the left of it. And we see that when it fissions, the normalized energy, the total energy, and really it's the free energy, which I'll define in a moment, is negative. And you see one implication of that is that even though it evolves, it can only evolve so far in distance before it runs into essentially a zero velocity surface, which is represented by this red line and this constant energy here. So this guy is trapped. It's unstable, but it's trapped. If we move over to the case where the mass fraction is less than this 0.17, over in this region here or up in this region here, the topology of these curves actually changes at some point. And in fact, at that limit, the energy of this unstable equilibrium actually passes through zero in terms of the free energy and becomes positive. On that side of the limit, what it means is that if you actually have a body that fissions, it starts off its life at this energy level, and actually it's completely free to escape. And these two bodies can in fact escape from each other if they transfer sufficient angular energy from their rotational modes into their translational modes. That initial movie that we saw of 1999 KW4, that system in fact has a positive energy. And if I run that movie, that simulation long enough, those two systems will actually eventually escape, where enough energy gets transmitted to the orbit from the spin states so that they actually escape. There are other things that can happen too. However, if it does dissipate energy through some process, it can still end up in a stable equilibrium, which by definition always has to have a negative energy level. So that plot I showed was actually an idealized plot. That's why it was so smooth, made for spheres. In assuming that maybe there's some small tidal flexure that transfers orbital torques across each other. However, the theory works very well for arbitrary shaped bodies. And here we've got plotted on here, appropriately scaled, the sphere-sphere system, the red line, and variants of other shapes and sizes, just looking to see how everything scales. And you see some variation around that line, but the essential fact holds true in terms of there being a consistent, stable, and unstable region. Similarly, for the energy line, that line can move a bit higher or lower energy depending on peculiarities of the shape. However, consistently and qualitatively, this result still holds true. So it's something that we can actually use the sphere system as an analog for understanding what goes on here. And then I've mentioned the free energy. If we make the assumption that once the body separates and splits, if the self-potentials of those two components of the body are actually conserved and don't change, we can actually remove them or subtract them from the total energy, and then we get this, what we can call the free energy, which just consists of the rotational kinetic energy, the translational kinetic energy, and the mutual potential energy between those two. And here we realize that if there is an escape of these two bodies from each other, the mutual potential goes to zero, and that can only occur if this free energy, in fact, is positive. So if the free energy, the total energy minus those two self-potentials is positive, the system can actually disrupt and go from resting configuration, where it was in an unstable equilibrium, into something where the two guys fly off into their separate orbits around the sun. If the energy is negative, however, it can't disrupt because the kinetic energy has to be positive, and thus the system would remain trapped for all time, and potentially could eventually dissipate energy and settle down to a stable state. It's interesting to note that if the free energy is positive but relatively small, the only way for the system to escape is for really the largest body to give up most of its rotational kinetic energy. And this is actually a marker for when this sort of a situation can occur. And in fact, we see this in nature, and I'll show you that in a little bit, where a system that has disrupted in this way tends to have a slowly spinning primary body left over, because the energy to escape had to come from somewhere. And in fact, that energy can be extracted from the rotational kinetic energy of the primary body. So here's a nice movie of the Okawa system, or an analog to the Okawa system, where here it is in its resting configuration, right before it actually spins a little bit faster and enters into this fission system. So what we found for this particular system is the total system energy is negative, but it's near zero. But that means that disruption is impossible, although since the energy is very close to zero, these two bodies can, over time, get very far apart from each other, although they always have to come back close to each other again. The re-impact is possible if the initial energy is larger than the fission energy, but if this guy is truly just fissions, then in fact this initial condition is a relative equilibria. And if you will, what we see when we look at the movie is that this system is actually moving away on its unstable manifold to that relative equilibrium. But it involves both translational and rotational motion. Given that, it also means that this guy should never be able to re-impact, because at best it could only, if it happened to be on a homoclinic trajectory, which I think it is, at best it could only asymptotically approach that equilibrium again, and it would take an infinite period of time. So this is the initial configuration. If it, for this level of angular momentum, if it dissipates all of its excess energy, it will settle into this configuration here. So this is the minimum energy at the same angular momentum, that minimum in the curve that we saw earlier. And then again, this is the movie of how the dynamics of this guy evolved initially. And yeah, it's just, I always like seeing this movie. Now here, there is no energy dissipation. And you'll actually see that the location of the secondary can go, of course, quite beyond that stable location. And really what this system is doing is exploring that constant energy surface, going to different radii, but is also trading it all with the mutual potential depending on the relative shapes of these two guys. And again, the interesting thing about the system is that it will follow these chaotic dynamics ad infinitum, because it cannot escape and it cannot re-impact. So it's a very interesting dynamical system. If perchance it did re-impact, the orbital speeds are very, very slow, on the order of centimeters per second, which is like not even that. So it's a very slow collision if indeed the collision occurs. So this is one of the initial implications that we can pull out of viewing these rubble pile systems with a simple model and as a celestial mechanics system. And it's that all contact binaries spun to fission are initially unstable. And this, for two bodies, it holds across all shapes and mass ratios. We also note from our direct numerical experimentation that the initial dynamics after fission are strongly chaotic and seem to really explore a large portion of that phase space. This is something that still has not been studied very closely, and I think would be a very interesting topic to consider at a deeper level. If we get a little more physically real and say, well, as these bodies spin relative to each other and interact with each other, there will be a lot of tidal flexure that occurs between these bodies, and that will dissipate energy in the system. You see from those movies that tidal dissipation that does occur is highly non-classical, because you have a lot of switching of the spin rates in one direction or the other direction, extreme changes in the distance and all that. So again, this would be a very interesting thing to study at a very fundamental level, especially during these early evolutionary phases. And again, for this particular problem, we're not been studied. The other implication is that contact binaries with a small enough mass fraction can mutually escape when spun to fission. So if the mass fraction is less than about 0.17, or conversely, if you view it as a mass ratio between these two guys, where a mass ratio of 1 would be an equal mass system, the mass ratio limit has to be less than 0.2. And this applies to all asynchronous bodies, and it sort of it means that it's difficult to directly form a binary asteroid system just by going through a spin fission event.